I typically like to start off by talking about something different that I've seen recently, or maybe got inspired to learn about, that involves organic chemistry, which is pretty much everything. And so I wanted to talk about a topic that was at the intersection of fashion and power and, of course, organic chemistry. And so let's go ahead and talk about the dye Tyrian purple. It's an organic molecule. My daughter in the 7th grade is mentioned that she was learning about ancient Roman government, the dynasties, and then the other forms of government with the Senate and stuff. And so it brought me back to thinking about Tyrian purple. Let's go ahead and talk about that. What is Tyrian purple? So Tyrian purple is a dye that is isolated from the organism that lives inside of these murex sea snail shells. So that's this kind of shell here. And there's a very particular gland in that shell where if you cut out that gland, it has this substance in it that isn't really purple. But when you crush that up and expose it to oxygen, enzymes inside of that organism will clip off this sulfate group enzymatically. And then in the presence of oxygen, this species will dimerize. Some really interesting radical chemistry. And then it undergoes one further oxidation. I've seen stuff that says it requires light and is a photooxidation. And it in that process of generating a carbon-carbon bond and oxidizing, they were doing this stuff like 8,000 years ago. It's amazing that they were, not necessarily the Romans at that time, but other peoples around the Mediterranean were forming carbon-carbon bonds and using organic chemistry in order to make this deep purple dye called Tyrian purple. I'm not sure if you can see that on the screen because my screen is black here. And so this dye was so incredibly difficult to isolate, right? You had to cut out this organism and then cut out a very specific part of the gland, that sea snail. And it would take about 10,000 of these shellfish to produce 1 gram of Tyrian purple dye stuff. And that was just enough dye stuff in order to dye the hem of one of these Roman togas. Those are the toga praetexta, is the one that was worn by kings or by consuls in the later Roman dynastic period when they had emperors. And so you get a sense for taking 10,000 of those sea snails just to dye the hem of that garment, how much effort that would have taken. And of course, if you were an emperor, then you wore a toga picta, which was where the entire robe itself was dyed with Tyrian purple. And you can imagine how many shellfish it would have taken in order to dye an entire robe or garment like that. Wow, the fantastic effort. And of course, dye stuff, the desire to want to synthesize dyes from cheap stuff like coal tar is what really drove the development of organic chemistry and led to the birth of the pharmaceutical industry. So very cool chemistry there. Cooler radical chemistry than you've learned about, unfortunately. I can't remember which chapter it was, maybe back in chapter 14 or 15 where you learned about radicals, but very interesting stuff. Okay, let's go ahead and continue off where we left off on Friday. I introduced you to 5 recipes for electrophilic aromatic substitution in order to form carbon-bromine bonds, in order to form carbon-nitrogen bonds, in order to form carbon-carbon bonds, in order to form carbon-sulfur bonds, and then one extra reaction for forming carbon-carbon bonds. And we're going to talk about these recipes today that can allow you to react with benzene rings that are normally so stable that the double bonds in benzene rings don't react with anything. And all of these reactions I'm going to show you, I already told you this, are going to go through the same 2-step mechanism. And the only difference for us really is going to be what's the nature of the electrophile that we're generating in each of these recipes, because you need a super aggressive electrophile in order to react with the double bonds in benzene rings. Let's go ahead and start off with the first reaction type, and that's going to be a halogenation of aromatic rings. So our recipe is bromine Br2, and we said we needed a Lewis acid catalyst for that. So what does this involve? Why would you want to do this? Why would you want to add a halogen to a benzene ring? There are some prescription pharmaceuticals, quite a few, that have fluorine atoms. We're not going to show you how to do that till the end of the course. And some that have chlorine atoms on them, like Paxil, antidepressant. But bromine atoms and iodine atoms, we won't show you that here. If you want to add chlorine or bromine, one of the most powerful things that you can do with that is something that we're going to show you that's a secret reaction. And we're going to show you the secret reaction when we get to chapter 20. So chapter 20, there's a super secret here that I'm going to show you. And that super secret reaction is going to take that carbon-bromine or carbon-chlorine bond and convert it into the most powerful nucleophile that you will learn about in the Chemistry 51 series. And that's a carbon-magnesium bond. We'll also show you a related metal you can put there, but it changes a carbon-bromine bond from something that looks like it has a leaving group to the most powerful nucleophile. And I can't resist telling you the secret here. It's magnesium. You just write Mg above the arrow, and magnesium metal will convert that into a powerful nucleophile. So that's why it's important to learn this. I promise you, you're going to need to know that for some synthetic reactions or questions on problem sets, on exams. I don't know where, but I'm sure that'll be important in my section and every section of Chemistry 51C, third quarter organic chemistry that's ever taught. Let's go ahead and talk about this recipe. What's the Br2 doing with this FeBr3? Let me go ahead and draw out the Lewis structure for bromine. And we have the Lewis acid in there in order to tug on one of those bromine atoms. The reaction starts with the formation of a bond between one of the lone pairs on one of the bromines and that iron atom. So we're going to go ahead and start off this reaction here by simply attacking that iron atom. There we go. I'll draw a curved arrow. And that now makes a bond. So let's go ahead and draw this species that you get. Let me make this bond a little bit longer, just so it looks like it's ready to break. And that ferric bromide species is now attached. I'll draw these other bromines on there just so you can see. We've turned this middle bromine in the middle here into a super great leaving group. Now I have to fix my charges. When I put a second bond on bromine, that turns into a bromonium ion. It needs a positive charge there. So let's go ahead and put that positive charge. Here it is. And if iron was neutral before, it better pick up a negative charge. That now has the correct charges, Br plus and Fe minus. And this whole thing that's that you see right here is now a super duper powerful leaving group. Let me write that here. Super leaving group. That's a super amazing leaving group. That's the point of having that bromine, form a bond. I'm not sure if I did a great job with drawing that. I'll circle the charge here so you can tell it's a negative charge and a positive charge. So we've made a super powerful leaving group. And so now it's going to be easy to do an SN2 reaction on this bromine that's at the very end. Let's go ahead and do that. I'm going to go ahead and draw out my benzene ring here, my starting material. If I have a benzene ring, those double bonds are just super unreactive. But now with this super powerful and amazing activated Br2 that we've generated, here's my FeBr3 attached to that bromine atom, making it just a great leaving group. I'll just write this out as a molecular formula. So plus, minus. Now it's so easy to attack that bromine on the end. Let's go ahead and do that. Let me use my glorious red color here for that. I find it distracting when this stupid palette comes up on my note-taking program on the iPad. I don't know how to get around. I don't know how to make it not show that, show you on the screen, that palette. But that's what happens. We end up forming a carbon-bromine bond by attacking that benzene ring. And so let's go ahead and draw that new species out. Now, it is absolutely critical that you don't forget that there was a hydrogen right here. So I'm going to draw it in the starting material. That's not necessary for the mechanism, but as soon as I draw that there, I know I'm going to remember to draw that over here in this next species. And if I don't, if I forget that for any reason, I'm going to be in trouble. So here's the carbocation that we generate. You can't tell from my arrow pushing that I was going to form which of these two carbon atoms in the double bond I was going to form a bond to bromine on. It's only when I draw this next intermediate that you can tell which carbon was going to form the carbon-bromine bond. So we now have this species that we've generated that's called an rhenium ion. I introduced you to that term rhenium ion before. And now we're going to pluck off this proton. It's so easy to deprotonate this. So easy. Let's go ahead and pull that proton off. And I'm going to use the lone pairs on this FeBr4 species, the leaving group. So, right, we've got any one of these bromines would do here. Let me go ahead and undo that little bond there that I drew. I'll just draw this again as a molecular formula, FeBr3. So this still has a minus charge. Don't try to use the iron to deprotonate, even though it has the minus charge. Use the lone pairs on bromine. That's what's really going to be pulling that proton off. So it's so easy to pull that proton off. Oh my gosh, this wants to be aromatic again. And I'm going to make my arrow end very specifically on that carbon atom. The book may show you to make it end on in the middle of the bond, which is fine, but our sapling system, I've made it so that there's only one way to answer the questions, and that's by making our curved arrows end on atoms and not in the middle of bonds. So I'm going to try to remember to always depict things in that way so that when we take our exams on sapling, it's like you're used to seeing it drawn, the curved arrows drawn, always in the same manner. And so now we've regained aromaticity, and it's a big sigh of relief for this aromatic, for this ring here, because it's now aromatic again. And you basically end up with HBr attached to FeBr3 as your byproduct. Okay, so, and if this were an arrow pushing mechanism and I didn't tell you what, you could write an A- for a proton transfer step. All right, this is the, so this is the mechanism. This is the first of the 5 reaction recipes. You need to know how you generate this electrophile and the mechanism for this 2-step electrophilic aromatic substitution. It's addition and deprotonation. Okay, let's go ahead and look at how you make carbon-nitrogen bonds to benzene rings. So remember, I told you that the recipe for this reaction is that we're going to have nitric acid, but we need a super powerful protic acid that we add in there. And so we add sulfuric acid. It's even more powerful, so powerful, more powerful than nitric acid that it can protonate the nitric acid. Let's go ahead and watch how that works. And why? Well, first, let me start off by saying, why would you want to do this? Why would you want to put a nitro group on a benzene ring? Pretty much, the only reason to put a nitro group on a benzene ring is to reduce it down to an amino group. That's what you really want on there. I tend to think kind of like a medicinal chemist, and medicinal chemists do not like nitro groups on their drugs because there's some sort of problem with toxicity and metabolism. Don't know all the details on that, but every medicinal chemist immediately wants to reduce that nitro group down to an amino group. And the way you do this, the secret recipe that I'll show you when we get to chapter 25, or maybe even in this chapter, is you just treat that with hydrogen and palladium on carbon. It's the same conditions that you use to hydrogenate double bonds, except nitro groups reduce even faster than double bonds do. It's such an amazing reaction to run in the laboratory. Okay, so let's talk about this recipe here, this recipe for nitration, so that we can really talk about what's going on. So I'm not going to draw out, let me go ahead and just abbreviate sulfuric acid as HA, and I'll spin it around because we're going to donate the proton. I really don't think you could ever guess the mechanism for this reaction if I didn't show you what that mechanism was. It just seems so counterintuitive. Here's the Lewis structure for nitric acid. It looks like this. There's a plus on nitrogen, and there's a minus on oxygen. And I feel like if you asked me, every part of my being would want to make a lone pair on the O minus pick up a proton. And that is happening in the reaction. That's happening. The O minus is getting protonated, but that doesn't lead you down the pathway, the reaction pathway towards electrophilic aromatic substitution. It's only when you protonate this oxygen that you actually start towards the pathway towards electrophilic aromatic substitution. Let's see the consequences of that if we protonate this HO group. So I'll transfer the proton over there. I apologize for how crummy my drawing is on this iPad. I just got the iPad, I'm learning how to draw on it, and I feel a little awkward, so I'm sorry for the messy writing here. So you protonate that nitric acid, and so now we've generated a really great leaving group here on this nitric acid. Water is now a leaving group. Boy, it was tough to put that proton on there. And by protonating that oxygen, we end up with a situation that I don't ever want to see you do again in any other mechanism in this course. We end up with a situation where we have 2 formal positive charges. Now the net charge on this molecule overall is only +1 because there's 1 minus and 2 pluses. But you should be super uncomfortable if you ever end up with a resonance structure or some structure that has 2 positive charges. Don't ever do this again on any other mechanism in this course. But here, just to give you a sense for how stressed out this species is, now the lone pairs that are over here on that O minus can come into play, and they're going to push out that water leaving group. There we go. And I'm going to make the arrows end on the nitrogen atom, and now I'm going to break that bond and give the electrons back to oxygen. And so when we do this, we're going to generate a small intermediate amount of this species that should look weird to you, that you've never seen before. The species called a nitronium ion. Nitronium ion, there we go. That's the nitronium ion that we've generated here. Let me go ahead and circle or underline that just to emphasize that's the nitronium ion. And that's the super reactive electrophile that's going to add to a benzene ring. So let's go ahead and draw out our mechanism for electrophilic aromatic substitution. We've got our 6-membered ring here. And we've got our nitronium ion. There it is, just floating around. It's so reactive. Oh my gosh. You know, if water, you know, the water that we generated here is going to re-add back in, and it will take you back and forth between protonated nitric acid and nitronium ion. But every once in a while, this is going to bump into a benzene ring. And so then we're going to add to the double bond of a benzene ring. I can push the electrons to either oxygen atom. I'll choose to break the bond on the bottom. It's arbitrary. And now we generate this arenium ion intermediate. You know, it's got resonance stabilization. Arenium ions have resonance stabilization. I'm going to draw the proton on the top this time. I'm not quite sure why. We don't really need to worry about the structure of that nitro group, so I'll just write it as a molecular formula. What we need to worry about is how are we going to get that proton off? I'm just going to write A minus here to represent a symbolic conjugate base here to pull off that proton. It's really probably water under the conditions of this reaction, you'll recall. But here, for an arrow pushing mechanism, we can just symbolize bases as B if it's basic conditions, or bases as A minus if it's acidic conditions. Let's go ahead and pull that proton off. It really wants to be aromatic again. There we go. Now we regenerate the double bond in this reaction. And so we get back aromaticity, and now we've got a nitrated benzene ring. And we're just ready to reduce that nitro group down using palladium and hydrogen gas. We'll show you a second recipe for reducing nitro groups down, but what a great reaction to put nitro groups on benzene rings. All right, that's how to make carbon-sulfur bonds. How do we do that? This is not, again, this is not the order that I showed those 5 reactions to you before, but I think this is the order in the book. So carbon-sulfur bonds really used to be important, especially in the 1930s when they first started writing, you know, I guess that led to the, maybe it was a couple decades later, they started to put out the first really popular organic chemistry textbooks. So they just really love to talk about putting sulfonyl groups on benzene rings. It's not quite that common anymore as it used to be. One place where you've seen benzene rings with sulfur attached is tosyl chloride and making tosylate leaving groups. So this whole tosyl chloride and tosylate leaving group is derived from toluene sulfonic acid. And we make this using electrophilic aromatic substitution, using this secret recipe that I mentioned to you before. And that is sulfur trioxide. And again, we add this super powerful protic acid, sulfuric acid. I think, you know, really the first organic textbooks that were written maybe 40s or 50s were really inspired by the fact that the pharmaceutical industry had just come out with a powerful, well, not so powerful anymore, but what seemed powerful at the time set of drugs called sulfa drugs that had these kinds of benzene rings with sulfonyl groups on there. I think the first one was Prontosil. You can see back in the 1930s, they sold these in packages that made it look like the way we package candy now. But let's go ahead and talk about this mechanism. It all starts off with our secret recipe for forming electrophiles. So let's go ahead and draw out sulfur trioxide. It's sulfur, it's trigonal planar, it's got 3 bonds, there they are. They're double bonds to oxygens. And we add sulfuric acid because we want to protonate this thing to make it even more electrophilic. Let's go ahead and draw out, and I'm not going to draw the structure of sulfuric acid. I expect you to know the structure of sulfuric acid. It's kind of like toluene sulfonic acid with an OH instead of an aryl group. And we're going to protonate this sulfur trioxide. Now I could draw the sulfur trioxide starting from the oxygen atom lone pairs. That would make a lot of sense, but I think I'm going to choose in this particular case to depict this by using the double bond to protonate, to pick up that oxygen and protonate to make an OH bond. And the reason I wanted to depict it this way instead of sticking the oxygen, the proton right on an oxygen lone pair, is because I just want to emphasize that this makes the sulfur more electrophilic. So I get right to the resonance structure that I'm interested in here. And that's the resonance structure that has S plus and an OH attached. So we really make that sulfur atom electrophilic when we protonate one of the 3 oxygens of sulfur trioxide. And of course, this is putting a proton on, taking it off. So we've generated our super powerful electrophile. Let me go ahead and draw the 2-step mechanism again for electrophilic aromatic substitution. Here we go. And we've got our protonated sulfur trioxide. I'm just going to depict it like this for now, just to save a little space. There's a positive charge on sulfur. And let's go ahead and push those arrows again. We're going to protonate one of the double bonds. I start from the middle of the double bond when I do curved arrow pushing. And now we've generated a carbon-sulfur bond on our benzene ring. This is our rhenium ion intermediate. So now we've got sulfur, this sulfonic acid. That's the name of the functional group. It's a sulfonic acid. We have that proton right there at the position where we form the carbon-sulfur bond. So this is really stressed out. It has lost aromaticity, way less stable, what, 10 to the 24 times less stable than the starting material. So it's super stressed out, really wants to be deprotonated so it can become aromatic again. And so something pulls the proton back off. Anything with a lone pair that's in that solution, we're not going to worry about what it is. I'll just draw a conjugate base from our acid because the conditions are acidic, and then I'll give those electrons to the carbon to regenerate our aromatic ring. So here we go. We've got this particular molecule would be called benzene sulfonic acid. Now I'm going to draw the full Lewis structure here. Well, not the full Lewis structure. I won't draw the H's. But I'll draw out the sulfonic acid functional group so that you can see it. And that's the way they make toluene sulfonic acid, which we're going to use as a Lewis acid or as a protic acid catalyst later on when we get to chapter 21. Wow, so we've got carbon halogen bonds, carbon bromine bonds, and it's for the bromination, it's the same mechanism for chlorination. And now we've got carbon nitrogen bonds with nitration, and now we have carbon sulfur bonds available via this sulfonation reaction. And so let's go ahead and talk about the next reaction, which is formation of carbon-carbon bonds, and that's exciting. So boy, every synthetic organic chemist just loves forming carbon-carbon bonds. We'll get to the real way that chemists and nature forms carbon-carbon bonds in a couple of chapters, but if you want to make drugs, substituted benzene rings are pretty common in drugs. And this is one of the main ways to form carbon-carbon bonds. So I mentioned to you this species, this reactive species that you haven't seen before that's going to be so important in this quarter. They're called acid chlorides, or the newer, more IUPAC strict description of that would be an acyl chloride, which may be what the book uses. So an acyl chloride. Let's go ahead and talk about what's going on in this reaction. So we use a powerful Lewis acid here, aluminum trichloride, which is more powerful than FeBr3. If you threw FeBr3 in here, it would tug on the chlorine, but not enough. So we use aluminum for this one, and aluminum trichloride. So you have to keep those Lewis acids straight. Right? FeBr3 wants lone pairs on halogens, aluminum trichloride wants lone pairs on halogens, but this is the one you use for Friedel-Crafts reactions. So, and that's named after the inventors of this aromatic substitution reaction. I don't remember the first names of these folks, Friedel and Crafts, unfortunately. So let's go ahead and draw out the general mechanism for how does the aluminum trichloride activate this acyl chloride functional group. So I'm going to abbreviate, because it doesn't matter whether it's an isopropyl on this acyl chloride, or a benzene ring, or ethyl, or methyl, or butyl. It's the same mechanism. So we've got our chlorine atom here, and then we've got our Lewis acid, aluminum trichloride. There it is, aluminum trichloride. And it adds to the lone pairs. It adds to, there's oxygen lone pairs there that are actually more reactive towards coordinating with aluminum, but that doesn't lead to any productive reaction. It'll pop off the oxygen. If aluminum adds to an oxygen lone pair, it'll pop off again, over and over. And eventually, we'll end up forming a carbon-chlorine bond. And when you form this bond, now it's got something extra that it can do that leads to an amazing electrophile that's going to freak you out. So here's the electrophile that we generate. I don't know, why did I choose to draw the carbon atom there? I don't know. There we go. And so now we've really activated that chlorine and converted it into a chloronium ion. That's a Cl with a plus charge. Here's that aluminum that's on there. And I'll kind of do it the way I did with the, I'll draw it so you can see that it's kind of a tetrahedral leaving group. If aluminum was neutral and now I poke another bond in there, it better become an aluminate with a negative charge. And the chlorine now has a positive charge. That we would refer to that as a chloronium if the Cl has a positive charge. 2 bonds to chlorine better have a positive charge on there. So now we've turned this into a super leaving group. That was kind of similar to that FeBr3 thing. Let me write that down there so we get a, just so we remember that this thing right here, super leaving group. We'll just write super leaving group. Wow. So it was worth forming a bond to that chlorine and stressing it out by doing that. And so now the lone pairs on the back end here, let me draw the lone pairs on this back side, opposite side of that chlorine atom. Now those lone pairs can push out this amazing leaving group. We're not going to do SN2. When I call it a leaving group, doesn't mean we're going to do SN2. Well, you're really, if you're thinking that when you hear the word leaving group, you're really like 10 chapters behind the times here. We're mostly moving beyond that kind of an SN2 process. Let me go ahead and push out. So excited to push out this leaving group because, and I'm going to attack that carbon atom and give the electrons to the chlorine. And when we do that, we generate this weird looking species. I hope it looks weird to you. You've never seen anything like this before. Look at this. You've got a carbon, 3 bonds to oxygen. Doesn't that freak you out? That's called an acylium ion. Critical intermediate here. It's called an acylium ion. And you may think, well, that looks so strange to me. I've never seen anything like that. But you know what? Every single second row atom here satisfies the octet rule. Oxygen has 8 electrons, 2 in each bond, and then a pair of electrons in a lone pair. The carbon atom has 4 bonds. That's 8 electrons. Every atom in here, as freaky as that looks, at least it satisfies the octet rule. So could be worse. And then you end up with as a byproduct here, this tetrachloroaluminate. I'm not sure whether I need to draw this out. I'll draw it out there for you anyways. So it's tetrahedral and it's got 4 bonds to chlorine here. I'll circle the minus. That's a really poorly drawn minus charge. Let me try to erase that and do that over. I'll just put a negative there. So that's a tetrachloroaluminate leaving group. But we've got this acylium ion. Let's use that for electrophilic aromatic substitution. I just feel like I really want to do electrophilic aromatic substitution with that. So we've got to draw our benzene ring, and it's going to be the same 2-step mechanism that we've seen before. And all we're really doing is we're changing the electrophile. So let's draw out our acylium ion here. So here's our acylium ion. Put the positive charge on the oxygen, right? And you might think, oh, gee, if I've got a positive charge on oxygen, that means I need to attack the oxygen. Absolutely not. Absolutely don't attack the oxygen. What you do is you attack the carbon atom and push the electrons up to oxygen. There we go. And now we're going to push the, now that's how you satisfy the oxygen atom, right? The oxygen, if you want to get rid of that positive charge, this is the only way to do it. Attacking the oxygen directly with the benzene ring wouldn't get rid of that positive charge. Okay, so we've formed a carbon-carbon bond and generated an acylium ion. Here's that acylium ion. Let's just draw that functional group in there. There it is. Oh yeah, carbon-carbon bonds. Awesome. And it's an rhenium ion. It really wants to be deprotonated. Something's going to deprotonate it. I'm going to draw this leftover A minus. The conditions are acidic, so I'll draw a conjugate base left over for just a symbolic conjugate base. Let's go ahead and pull that proton off. And I'll take those electrons and give them right to that carbon, right there. That's the way we'll be depicting that. Right, if you do something on sapling, we'll make the curved arrow end on the atom, not on the bond. Even though it's, you know, when I normally outside of sapling, I would make the arrow end on the middle of the bond, but this is the other way to depict that. Okay, so we've regenerated aromaticity, we formed a carbon-carbon bond, and really that's super fantastic. Organic chemists love carbon-carbon bond forming reactions. And you can just take a benzene ring and substitute one of the H's, this H right here, you can substitute that with a carbon atom. That's fantastic. Okay, we have one more recipe here to think about. I showed you, what have I shown you before? I've shown you how to make carbon, bromine, and chlorine bonds through that Br2, FeBr3, or you could use Cl2 and FeCl3. I showed you how to nitrate benzene rings using nitric acid and sulfuric acid. I showed you how to sulfonate benzene rings using SO3 and H2SO4, sulfur trioxide and sulfuric acid. And then I just now showed you Friedel-Crafts acylation to put carbonyl groups directly onto benzene rings. And really, carbonyl groups, that's the name of the game for chapter 20, chapter 21, chapter 22, chapter 23. You're going to need carbonyls all over the place. So that'll turn out to come in handy, being able to put carbonyl groups directly onto benzene rings. Okay, we have another Friedel-Crafts reaction called the Friedel-Crafts alkylation, not an acylation. And it's basically the same recipe as the Friedel-Crafts acylation reaction was. This one instead, where you're going to use alkyl chlorides. You could use alkyl bromides, you could use alkyl chlorides, alkyl iodides, not fluorine, but you wouldn't see that anyways. And so, again, we're going to use aluminum trichloride to rip a halogen atom right off of that alkyl chloride. That's the point of the aluminum trichloride. Let's go ahead and walk through that mechanism. It'll look eerily similar to that acyl chloride acylation reaction, except we don't go through an acylium ion. So maybe this one will be a little bit more in tune with the kind of chemistry you saw in Chemistry 51A. Let's go ahead and draw out that alkyl halide. I'll go ahead and start by drawing the lone pairs right on that chlorine because that's what the aluminum is going to tug on. And so now I'll draw our aluminum trichloride. Here we go. I haven't decided how, using this Apple pencil thing, how to draw my L's. You can see I'm still in the process of, it's such a slippery Teflon surface. I don't feel like I have a natural way yet to draw L's. It's hard to explain why that just feels weird to me with the Apple pencil. I've spent 2 decades learning to write with chalk, or maybe 15 years learning to write with chalk, and then another 10 years learning to write with those whiteboard markers. And now I have to switch again. It's kind of hard to get you know, no problem. You guys learn new stuff, so just bear with me if my handwriting just seems absolutely atrocious. I just feel kind of childish now, learning how to write with an Apple pencil. Okay, so we generate this species. We've turned this chlorine atom to a great leaving group. That's now a chloronium ion. We have to put a minus charge on the aluminum. We just added a new bond to aluminum, and it was neutral before. And I already told you that this group here is just a super leaving group, super duper. So super duper leaving group, super leaving group. That's a great leaving group. Now it's so easy to walk away. And so we're just going to ionize off this chlorine atom and give the electrons to Cl. Ooh, let me use my red, my amazing red color here. And we're just going to take those electrons from that bond and give them to the chlorine, make it happy. And so in the process of doing that, we generate a carbocation. Man, it is hard to generate secondary carbocations, but this recipe can do it. There's the secondary carbocation. You know, for some reason, whenever I draw carbocations, I feel like I want to see all 3 things attached to the carbon atom. So I can't resist doing this. I feel like I have to draw that H there. Even though we don't have to draw the H's, I just like to see visually with my eyes. When I'm looking at a carbocation stability is so important. I want to see all three things attached, even if it's an H. So pardon me for drawing that in. That's just the way I like to draw carbocations, where I can see everything attached. So let's use that carbocation for electrophilic aromatic substitution. And here's I'll spin it around in the other orientation. There's our carbocation, our secondary carbocation. Boy, that is reactive. It is hard to generate secondary carbocations. So tertiary, no problem. But secondary, you need this. It really helps to have this special recipe. So now we attack that carbocation that we've generated with the aluminum trichloride. We make a carbon-carbon bond. And there's our carbon-carbon bond. And let's just remember, we still have a proton on that position that I hadn't drawn before. There it was. And so we generate an uranium ion that's got a proton ready to be plucked off. And it's ready to be plucked off because I remembered to draw it there. And the conditions are acidic. So something with a lone pair under these conditions. I'll depict it as A minus. Just something with it's the tetrachloroaluminate byproduct that got popped off here. But we don't really care about that, the identity of that species. We just want to indicate that something's going to pull that proton off because this wants to be aromatic again. And there we go. We've pulled off the proton. And substituted our benzene ring with an alkyl group. That may look more, because you're not really familiar with carbonyl compounds, this may look more interesting and useful to you than the acylation, but trust me, it's not. You know, once you put an alkyl group on there, you're kind of, okay, now what? But when you put carbonyl groups on there, as you'll see from chapters 20, 21, 22, 23, 24, we want carbonyl groups on things because that's really the way synthetic chemists and the nature, and that's the way chemistry works. Most organic chemistry is with carbonyl groups. So the other problem with this reaction is that there's all kinds of substituents. When you put them on the benzene ring first, you can no longer do Friedel-Crafts alkylation reactions and acylation reactions. And the problem with alkylations that really makes them not very useful is you have to use your aromatic ring starting material in excess as a solvent. So it has to be so cheap that it's okay to use it as a solvent. And really that restricts this reaction to kind of benzene and toluene and maybe a couple other simple aromatic rings that you can buy as solvents because they're so cheap, and really limits the utility of the Friedel-Crafts alkylation reaction. Okay, so that's the 5 recipes, the 5 reaction recipes that we've learned. I'm going to show you one more way that we can do the Friedel-Crafts alkylation reactions, because you can generate carbocations in other ways. So back in chapter 10, you learned that you can protonate alkenes to make carbocations, and usually things would add to the carbocation like water or a halogen. But here I'm just going to show you that we can make carbocations, for example, by protonating alkenes. So if we look at this recipe here, we're using what ought to be a familiar recipe to you, and that is to protonate an alkene. So I think you should know that if we have some sort of an alkene in the presence of a strong acid, you wouldn't use hydrochloric acid here because you don't want the chloride anion to add back in to the carbocation that we generate. But under acidic conditions with sulfuric acid, you protonate alkenes. In this case, you put a proton on the least substituted carbon so that you can make a carbocation at the more substituted carbon. And so this process in the presence of sulfuric acid will generate a tertiary carbocation. You don't protonate the middle carbon to make a primary carbocation. And then that will do electrophilic aromatic substitution, just like an alkyl chloride we generated using an alkyl cation that we generated using aluminum trichloride. So, right, we generate a carbocation, we do electrophilic aromatic substitution, and I'm not going to show you all the steps. I just finished 5 times showing you this 2-step process, but you go through an uranium ion, and then you go through, I'm not going to show you those again, but you get the idea. If you generate a carbocation, whether it's using aluminum trichloride or protonation of an alkene, it will go through electrophilic aromatic substitution. Now, you got to be very careful with carbocations. I'm not sure if they mentioned this enough, but one of the big problems with carbocations, for example, if you try to make unstable secondary carbocations or super unstable tertiary carbocations, you have to worry about the potential for rearrangement. So if you tried to do our Friedel-Crafts reaction with aluminum trichloride, I'll just write that here. Aluminum trichloride, as the second you generate a primary carbocation here, that's going to try to rearrange. You could rearrange a methyl group, in this case the hydrido group. One of these three bonds next to that primary carbocation is going to migrate. The lighter hydrogen atom migrates faster generally if there's a choice, unless there's some conformational restriction. And so this hydrido group would migrate over in order to generate a much more stable tertiary carbocation. Faster than any benzene ring could ever attack this, the hydrido group would migrate. Now, is it possible the hydrido group could migrate back? Yeah, but I can't draw that equilibrium arrow small enough. It really would be so fast, super fast, so fast that you couldn't get a benzene ring to attack that carbocation. It wouldn't be fast enough. So the only thing that would happen then would be if you had benzene rings floating around. I'll write Friedel-Crafts here. If you did this in the presence of benzene rings, it's the tertiary carbocation, the rearrangement product, that would react in this case in order to give you Friedel-Crafts substitution. So you have to really watch out for, I kind of ran out of room here, so I'll try to tip up my T-butyl group a little bit. So you really have to watch out for the potential watch out for rearrangements of primary, most importantly primary, and then also secondary carbocations. If they can rearrange to tertiary, they're going to rearrange to tertiary before you can add to a benzene ring. And that's not necessarily what you want to happen in those cases. Okay, let's go ahead and talk about, we've got to get ourselves ready for what happens if there's already a substituent on the benzene ring. And this is like half of this chapter. The easy part of this chapter is memorizing those 5 recipes. The harder part is when you want to make an interesting substitute aromatic, you have to worry about what happens if there's a substituent there. We have to worry about something called regiochemistry. So here's an example. This starting material over here on this side is called toluene. That's toluene. And if we do electrophilic aromatic substitution, if we did nitration, if we did sulfonation, if we did chlorination in this case, is the chlorine atom going to go next to the methyl group, or kind of over here at this angled position, or is it going to go opposite the methyl group? All 3 of those are possible, and we have to sort out those possibilities, and you have to know how to use this. We have names for these substitution patterns. When the 2 substituents are directly next to each other, we refer to that as an ortho substituted arrangement. And I would refer to this as ortho chlorotoluene. And everybody would know that that means the chlorine is right next to the methyl group. When the chlorine is one away from the other substituent, we refer to that as a meta-substitution pattern. And then finally, when the chlorine is on the opposite side of the benzene, we refer to that as a para-substitution pattern. And so I want to explain to you how different substituents affect the rate at which each of those 3 positions reacts. Some of these are kind of symmetrical, so there's 2 equal ortho positions in this case and 2 equal meta positions. So I'm only gonna list the positions on one side, but because it's got a symmetry to it. Don't worry about the fact there's another ortho position on the other side. Let's take a look at what happens when we have a methoxy group on there. Somebody went through and measured how fast is it for you to add an electrophile to each of the positions in these 5 substituted benzene rings. They don't all substitute at equal speeds. So if you have a methoxy group, and the thing that makes the methoxy groups exceptional here is that there's a lone pair on the methoxy group. That oxygen, or if it was nitrogen with a lone pair, speeds up substitution at the ortho and the para positions. So if you chlorinated this, you'd get chlorine at the ortho and the para positions. If you nitrated this, you'd get nitro groups. Some of your products would have the nitro group at the ortho position, and some of your nitro groups would have a product at the para position. But the amount of nitration or substitution at the meta position would be so small, you couldn't even measure that in your product mixture. So whenever you've got heteroatoms with lone pairs, they tend to favor substitution at the ortho and the para position. Turns out that alkyl groups, methyl, ethyl, propyl, butyl, those are also, they also speed up substitution at the ortho and the ortho and the para position. And there's a little bit of a speed up, but it's so hard that it's hard to measure of the meta position. So if you isolate the products for nitration of toluene, you're going to get some of your products going to be ortho nitrotoluene, and then some of your products going to be para nitrotoluene. And the amount of meta nitrotoluene in there is going to be so small you couldn't isolate it or measure it because there's so much of the other stuff. Now, if you just have a proton, all the positions are the same and the relative rates of substitution are the same. What happens if we take a halogen like bromine or chlorine, or fluorine is not really an important one for these types of reactions. We won't learn about that. But if you have a bromine or chlorine on a benzene ring and you substitute this with nitration or acylation or something like that, what would be the speed at which you substitute? It turns out that every position substitutes more slowly than a benzene ring, but some positions are slowed down more than the others. Now the ortho and the para positions are slowed down more than the meta position. Everything's slower, but the ortho and the para positions are slowed down even more. And so by default, you get, sorry, I'm skipping ahead of myself. The ortho and the para positions are still, because of the lone pair, are still substituting faster than the meta position. And so you end up getting almost all ortho and para substituted product and very little of this meta substituted product. It's nitro groups that have no lone pairs on the nitro, or a carbonyl group that has no lone pairs on the carbonyl carbon. Those slow down at the ortho and the para position so much. They get so much slower that the only product that's left is the product of substitution at the meta position. So I've shown you these classes of groups here, right? Don't count the original protonated ones. Most of them favor substitution at the ortho and the para position, but a special kind of electron deficient group, we're going to go into great detail about this coming up in our next lecture on Wednesday. We're going to talk about why some groups favor, how to rationalize how some groups deactivate ortho and para substitution so much that you're left with substitution, slow substitution at the meta positions. It'll be a big theme trying to explain that stuff coming up.